Before proceeding with the installation, configuration, operation, or maintenance of these products, please ensure you have thoroughly reviewed all relevant documentation provided by Balluff and other pertinent sources, including installation guides, configuration manuals, and operational protocols. It is essential for users to adhere strictly to all applicable codes, laws, and safety standards during installation, wiring, adjustment, and operation. Installation, configuration, use, assembly, disassembly, and maintenance of these products must be performed by individuals who have received appropriate training and are fully versed in following the outlined procedures and safety measures. Failure to comply with these prerequisites may result in noncompliance with legal and safety standards. We expressly disclaim any liability or responsibility for damages, whether direct, indirect, special, or consequential, arising from the use or application of the information contained herein. Balluff Inc., in no event, will be held accountable for any damages incurred as a result of using this guide. The content of this guide is intended for illustrative purposes only and does not ensure suitability for specific applications due to the diverse range of variables and requirements in different scenarios. Users are entirely responsible for verifying the applicability and safety of this information for their unique situations. Acceptance and use of this information come with an understanding that any and all risks associated with the installation, configuration, assembly, or use of these products are fully assumed by the user. Please note that this document does not serve as a warranty of any sort, nor does it modify or supplement any valid warranty provided by Balluff Inc. for these products. The information herein supplements the original warranty terms without altering
In
them.
this video, we will go over how to read process data from a Balluff Modbus TCP I/O Link master module. Our network layout consists of having a Balluff Modbus TCP I/O Link master connected to a PC running Modbus TCP client software. Connected to the I/O Link master module in the first port is an I/O Link condition monitoring sensor. Connected to the second I/O Link port is a Balluff configurable discrete I/O Link hub. On that hub is a discrete input sensor. The Balluff I/O Link master is already configured for I/O Link communications. Starting at Modbus register 3000 is the I/O Link port diagnostics. This register will show if there is any voltage short circuits, actuator warnings, along with any I/O Link short circuits. Modbus register 3001 will show whether I/O Link communications is established and also whether there's valid I/O Link process data going into the module. Register 3004 and 3005 will show port actuator shutdown as well as port actuator warnings on pins 2 and 4 for all the 8 ports. Next, we'll open our Modbus TCP client software. This client software simulates similar to what a Modbus TCP PLC or any other Modbus client software would behave. We could type in the IP address of the Balluff I/O Link master module. In this case, it's 192.168.1.1. The Modbus TCP port would be set up as 502. We could set up a timeout and a delay between polls. All Modbus register reads will use Modbus function 03 read holding registers. The slave ID is set to 1. The register start address we will be looking at for the port diagnostics is 3000. We will be looking at 5 registers. We could also set up a pull rate of 500 milliseconds. When we hit the connect button, we could see that register 301 has values being returned. To properly display the value, we could select display and look at it in binary. From here, register 3001 shows that I/O Link communications has been established, and this is for all ports for bits 0 through 7. So looking at this value, we could see that port 1 and port 2, which we have our I/O Link devices on, has a value of 1 being set to it. Next, the table on the right will show specific I/O Link diagnostics for each port. The N shown in the table represents the specific port's diagnostics. So for example, to look at port 1 diagnostics, this will start at register 3N or 3100. For port 2, it would be starting at 3200. And then for port 8, it would be starting at 3800. When we look at the actual values shown with Modbus register 3100, we could see a value of 3 being shown. If we look at display and look at binary, this shows that the I/O Link mode is set up as well as the device being connected. If we had set up validation or anything else on there, this would also show us whether we have a wrong vendor ID, device ID, or if we have an incorrect length in register 3100. 3101, the next register, shows the vendor ID. So in this case, the vendor ID is 888 in decimal. We could also look at that value in hex, which the vendor ID for Balluff is 0378. Then the next three registers will also show the device ID for the particular device that we have connected, as well as any event qualifiers or any events that have been happening on the device. The port on the IO-Link master module can also function as a discrete input or an output on pins 2 and pin 4. To access the data when using the port as a discrete, Modbus register 2000 will show pin 4 and pin 2 of the value of the digital input. Modbus register 2001 will show pins 4 and pin 2 of the 8 ports when it's set up as a digital output. Modbus function 16, write multiple register, will allow you to write to the Modbus output registers when trying to turn on a digital output. Here, looking at address 2000 for digital inputs, we could see a value being shown. You could also display this as a binary value, and from the binary value you can see byte 0 and byte 1 showing pins 2 and pin 4 of the digital inputs. If we were to access the digital outputs, we would start at Modbus register 2001. Modbus register 2001 shows the current digital output states of pins 4 and pin 2. In order to change this value, if we go into function and select write multiple register command, from here we can write a hex value and turn on, for example, pin 2. So pin 2 would be the high byte. So in order to turn them all on, we could write a value of FF. If we hit send, we would get an acknowledge that the write operation was successful. Here we turn on all outputs for pin 2 on the IO-Link master module. If we open up the web server, we should see this change. Here we could see that all outputs on pin 2 are turned on when we set the write multiple register command to turn on all pins 2 on the 8 ports. IO-Link process data will start at Modbus register 1100 for port 1, 1200 would start for port 2, and so forth up to Modbus register 1800 for port 8. Within those registers, the first register will show that the process data is valid. The next 16 registers after that, so in port 1, it would be 1101 up to 1116, will show the actual process data for that particular IO-Link sensor. Modbus register 1117 will then needs to be enabled in order to show that output data is valid. This, setting the value to 1, would validate your outputs. Then Modbus register 1118 up to 1133, with those 16 registers, would be the output data for the particular IO-Link device. Next, we'll use the software to look at the data on our IO-Link condition monitoring sensor that's plugged into port 1. So here, we use a read holding register with the starting address of 1100. The count would be 17 to show all the inputs. When we hit connect, we could see the data being changed. The address register 1100, being a value of 1, shows that the data is valid. The next 16 registers would be the data returned from this particular IO-Link sensor. Here on the web server, we can select the sensor, then go under process data to show that process data and the meaning behind it. If the IODD file has been uploaded into the master block, we can select process data IODD. Here, the process data gets broken down for what those bytes mean. So we could see that this condition monitoring sensor sends back a vibration velocity RMS of X, Y, and Z, which all show this floating value. So here, through the manual, we could see that each one of these velocities is a 4-byte float. If we bring back our software, we can use and select the 2 bytes in between. If we select display, we can look at the value as a float. Here, depending on whether your processor on your Modbus TCP tester is big Indian, little Indian, or if byte swap needs to be done. In this case, it looks like big Indian byte swap needs to be done in order to match up to the data that's being returned through the 2 registers. We could do the same thing for the next 2 registers by going into display and viewing it as a float, which is 32 bits. Again, you could see that the vibration velocity RMS value of Y, the value shown here in our PLC or our processor, shows that it's coming in as big Indian and the bytes are being swapped. And this is because it's using 2 registers, with each register being 16 bits. Next, if we want to look at the data coming in from port 2 for our discrete configurable hub, we can go back into our software, change the register value to 1200. The count can be set up for 17, and we could connect to it. Here, we could see the data that's coming back from our discrete configurable hub. On the web server, we can select on port 2 to look at the data. Here, under process data, we can see that the hub itself is only returning 2 bytes of data, and that the sensor connected through port 1 on the hub shows a 1 that the sensor is on. If the sensor is off, then this value should read 00. The process data through the IODD file will show us exactly which pin and which port that particular sensor has the on bit on. So through our client software, when we look at it, port address 1200 shows a value of 1, which shows us that the process data is valid for that particular port. The data, which is the 01, starts at register 1201, and here we can look at the register value. Otherwise, we could also display it in binary. Within that, then that would match up to the process data shown in the IODD file. Next, in order to write to any process data output for IO-Link process data, the first register at 1117 will need to set as a value of 1 in order to validate the outputs. Then the other 16 registers you can write the process data outputs to. So in our example, for the configurable hub, the register will need to start at 1217, will need to be validated with a value of 1 in order for us to write to any outputs on the discrete hub. Next, if we look on the web server on port 2 of our discrete hub, when we look at process data, we could see that pin 4 outputs is shown as invalid. And this is because the validity qualifier is turned off, as shown here. This is controlled through Modbus register 1217. In here, we could see that the value is 0. In order to make the process data output valid, we would have to set this value to 1. This can be done using Modbus function write multiple registers. When we write a value of 1 and hit send, we will get a prompt that says that the write operation is successful. Once successful, you could see on our web server now that the pin 4 outputs in order will show that it's 2 bytes output for this discrete hub versus invalid as it was shown earlier. Now, in order to write to the digital outputs, we can close the screen. The next digital output starts at the next register. Since it's only 2 bytes long, or 16 bits, we can write the register start value of 1218. From here, we can double click to write multiple register again. If we write a value to here and hit send, then that value 256 will show up as your output register. We can also write the values in hex if it makes more sense. So again, function write multiple registers, value type as hexadecimal, and we can write a value of FF, for example, to turn on all the bits. When we hit send, we get a successful prompt and then you could see that the FF value is shown here on the web server, which controls the discrete